Let's take a look at this review problem. I'm solving this initial value problem, y prime equals the quantity 3t minus 4y plus 5 squared. We're going to solve, and y of 1 equals 2. We're going to figure out how to get y of 2 and y of 5 numerically using a step size of 0.01 by these 4 different methods. And in this problem, we're not going to actually do all the hard work. In other words, I'm not expecting you to be able to do all the calculations on the test. That's a lot of work. But I do want you to be able to describe how you would do this given enough time. Okay, so first off, let's talk about Euler's method. So for Euler's method, the governing equation is y of n plus 1 is equal to y sub n plus h of f of t sub n minus t of n y of n, where the f function is the thing on the right-hand side. So in our case, this means that y sub n plus 1 is equal to y sub n plus h times 3t sub n minus 4y sub n plus 5 quantity squared. And the h that we've been chosen is 0.01. So this is the recursion that has to be implemented. And a simple way to do this is with a spreadsheet. So if I imagine column A, column B of a spreadsheet, column 1, row 1, row 2, row 3 of a spreadsheet, the initial condition is that y of 1 is equal to 2. So at time 1, the function is equal to 2. Then I increase my time by 0.01. So increase time, so a1 plus 0.01. Then in cell B2, I would have equals the previous y value plus 0.01 times 3 times the previous t value minus 4 times the previous y value plus 5 squared. And then I would fill down these columns in order to figure out the however accurate I want to make this. Now in the given problem, we're asked to figure out what y of 2 and y of 5 is. So if we're starting at 1, to get to 2, that's going to be 100 steps. And to get to y of 5, that's going a distance of 4 by steps of 100, so that's 400 steps. So to get to y of 2 is 100 steps. To get to y of 5 is 400 steps. So if I were to do this, if I go down to row 101, I would get y of 2. If I go down to row 501, I would get y of 5. And so that's the implementation of Euler's method. Okay, let's now take a look at how to implement the Taylor series method for solving this initial value problem. The Taylor series method is y sub n plus 1 is equal to y sub n plus h f of t sub n y sub n. Now if I stop there, that's Euler's method. The Taylor series method offers an extra term, 1/2 h squared, times the partial derivative of f with respect to t, evaluated at t sub n y sub n, plus the function evaluated at t sub n y sub n, times the partial derivative of y at t sub n y sub n. Okay, so to implement the Taylor series method, I've got a couple of derivatives that I have to figure out first. So first off, the derivative of f with respect to t. If I take the derivative with respect to t, I get 2 times 3t minus 4y plus 5 to the first, times the derivative of the inside, which is 3, with respect to t. So I get 6, 3t minus 4y plus 5. If I take the partial derivative with respect to y, it's going to look similar. The partial derivative of this with respect to y will be 2 times 3t minus 4y plus 5 times the derivative of the inside with respect to y, which is negative 4. So this works out to be negative 8 times 3t minus 4y plus 5. And so therefore, we have that the recursion relationship y sub n plus 1 is equal to y sub n plus 0.01 times 3t sub n minus 4y sub n plus 5 squared. Then the next term will be equal to plus 1/2 times 0.01 squared times the derivative with respect to t is this, so 6 3t sub n minus 4y sub n plus 1 plus 5, plus the product of the derivative and the original function. So we'll get minus 8, 3t minus 4y plus 5. Then I multiply that by the original function, and I get a cube. And so that is the recursive relationship that has to be implemented. Now, I could simplify this slightly by canceling out the half, but I'll just leave it as this. So to implement this in a spreadsheet, column A, column B, row 1, row 2, the initial value will be at y of 1, the function is equal to 2. I then step by 0.01 in time, and then the y-coordinate will be equal to the previous y-coordinate plus 0.01 times 3 times the previous t value minus 4 times the previous y value plus 5 squared plus 0.5 times 0.01 squared times this very large thing, which you'll have to write out, 6 times 3 times a1 minus 4 times b1 plus 5. I forgot that. Okay. Minus 8 times 3 times the previous t value minus 4 times the previous y value plus 5 to the third. And another parentheses, and that closes out this parentheses. And that is what would go in the contents of cell B2. Then for cell 3 and beyond, I would fill down to get the further values of y. Again, I would do this 100 times to get y of 2 and 400 times to get y of 5, so that y of 2 would appear in row 101 and y of 5 would appear in row 401. So that is what I'll need to type into a spreadsheet in order to implement the Taylor series method. Okay, let's now talk about how to solve this initial value problem using the improved Euler's method, using the predictor corrector. Now, the implementation of the improved Euler's method looks like this. Y sub n plus 1 is equal to y sub n plus 1/2 h times f of t sub n y sub n plus 1/2 h f of t sub n plus 1 y sub n plus 1. Now, there's a problem with this, which is this y sub n plus 1, of course, appears on the right-hand side. So to implement predictor corrector, I'll put a star on this, where the predictor here is what I would get by just using Euler's method. Y sub n is equal to h f of t sub n y sub n. So I do this first, and then whatever this is appears in this spot right here. So the implementation of this would go in 2 steps. So first, I've got the y sub n plus 1, the predictor step, has got y sub n plus 0.01, 3t sub n minus 4y sub n plus 5 squared. And then the actual value, so that's a tool that I use to get the actual prediction. So I correct this y sub n plus 1/2 times 0.01 times 3t sub n minus 4y sub n plus 5 squared. Then the second part, 1/2 times 0.01, 3t sub n plus 1, minus 4 times the thing that I found on the previous step, plus 5 squared. And so that would be how we would solve this initial value problem using the predictor corrected method and improved Euler's method. All right, now this is going to require a spreadsheet with 3 columns because I have 2 steps that I do on each step. So there's going to be one column that keeps track of the time, and then there will be a second column that keeps track of this predictor step, and then the third column is the real prediction. So A, B, C. And the real values that I care about are going to be in column A and column C. Okay, so I forward time by 0.01, In column B, I'll do what I have here. So it's going to be the previous y value, C1, plus 0.01 times 3 times the previous t value minus 4 times the previous y value plus 5. And so that would be Euler's method. Then over here in column C is going to be a bit of a mess, equals the previous y value plus 0.5 times 0.01 times 3 times the previous t value minus 4 times the previous y value plus 5 squared plus 0.5 times 0.01 times 3 times the current t value, so that's an A2, minus 4 times this predictor, in B2, plus 5 squared. And so that's all appears in cell 2, and then we fill down all 3 of these, and then column A and column C is what I care about. Column B is a step that I use in the between. The things that I really care about are going to be in columns A and column C for the implementation, for the answer that comes out from the improved Euler's method. And as before, this will have to be done to row 101 to figure out y of 2, and to row 401 to determine y of 5. Finally, let's take a look at the solution of this initial value problem using the Runge-Kutta method. The Runge-Kutta method is a fourth order method, and it is certainly the most complex of the ones that we've seen in this video. The setup is y sub n plus 1 is equal to y sub n plus h times kn1 plus 2kn2 plus 2kn3 plus kn4 all over 6. So there's 5 steps of computation. I've got to figure these 4 things out, and then the 5th step is to get y sub n plus 1. So in this example, k sub n1 is equal to f of t sub n y sub n. And in this problem, that's equal to 3t sub n minus 4y sub n plus 5 squared. Kn2 is equal to f of t sub n plus a half h, y sub n plus a half h times the thing that I just got, k sub n minus 1. So that's going to be equal to 3 times t sub n plus a half h minus 4 times y sub n plus a half h times the thing that I just got, kn1, plus 5 squared. Kn3 is going to be very similar to Kn2, except the last term is 1/2 h Kn2 instead of n1. And so in this problem, that's 3 times Tn plus a half h minus 4 times y sub n plus a half h Kn2 plus 5 squared. And then k sub n4 will be equal to f of Tn plus h, yn plus h times kn3. Now that's Tn plus 1, but I'll write it like that just so that it matches the form of all the previous terms. Tn plus h minus 4 times yn plus h times kn3 from the previous line, plus 5 squared. And so we figure out these 4 things, and then figure out this average, and then finally we get the real thing that we care about, y sub n plus 1. So implementing this in Excel definitely takes work, and this is going to require 6 columns. Okay, the first column is for the time. The last column will be the y value. Then I have 4 intermediate columns for the 4 intermediate steps in order to get that last value. So taking these one at a time, the t value will just increment by 0.01. then the b value here is going to be equal to 3 times the previous t value minus 4 times the previous y value plus 5 squared. And so that's what goes in column 5, or column B. Column C will be implementing this, so equals 3 times a1 plus 0.01 divided by 2 minus 4 times the previous y value over here in F2 plus 0.01 times the previous, the k thing that I just got over here in B2 divided by 2 plus 5 squared. And so that's what's in column C. Column D is going to look an awful lot like this. So the first part's the same, 3 times a1 plus 0.01 over 2 minus 4 times F2 plus 0.01 times, so H times, instead of B2, is now C2, because I'm using the KN2 thing that I just got, divided by 2, plus 5 squared. Okay, column E will be equal to 3 times A1 plus 0.01 minus 4 times F2 plus 0.01 times D2, the thing we just got over here, plus 5 squared. Okay, then once we have these intermediate values, we then have to take the weighted average and add to the previous value. So the previous y value, F2, plus 0.01 over 6 times KN1 is in B2, then 2 times KN2, which was in C2, plus 2 times KN3, which was in D2, plus KN4, which was E2. And then filling this down provides the fourth order estimate for the values. So there's row 1. Row 2 is this very long thing. And then row 3 would be starting with the arrows. So that is the handwritten way of implementing the Runge-Kutta method.